So constant surface temperature boundary condition for internal flow is quite a bit different than that for external flow. Okay, so if I have a constant surface temperature up here, and I have a mean temperature of my fluid coming in, mean temperature for my fluid coming out, okay, then these expressions for the amount of heat transferred into my fluid, okay, are going to depend on some delta T. But what delta T is that? I have temperature at my surface is constant all the way across, right? But this delta T at the inlet is different than this delta T at the outlet. Okay, so the question is what we use. Well, we've got two expressions, right? We've got H times A times delta T, okay? And we've got M dot Cp delta T. Okay, the question again is what are those delta T's if the surface temperature is constant? Okay. Well, in this case, this becomes a log mean temperature difference, and we worked on that a little bit in class. Okay, where our log mean temperature difference is equal to the delta T at the outlet, where this is the delta T at the outlet, which is equal to our surface temperature minus our mean temperature at the outlet. And this is our delta T at the inlet, which is equal to our surface temperature minus our mean temperature at the inlet. So this delta TLM term, the log mean temperature difference, becomes delta T at the outlet minus delta T at the inlet over the natural log of the delta T at the outlet over the delta T at the inlet. Okay, simple enough. Okay, and this becomes our mass flow rate times our heat capacity times delta T at the outlet minus delta T at the inlet. Okay, so these are the two expressions that you're going to use for constant surface temperature. Again, it's quite a bit different than what you see for constant heat flux. Okay, and so if we combine these things, okay, if we set these two things equal to one another, what comes out is that the surface temperature minus the mean temperature of the outlet over the surface temperature minus the mean temperature of the inlet is equal to the exponent of negative perimeter times length, right, where this is the length, divided by our mass flow rate times our heat capacity times our average convection coefficient. Okay. Likewise, if we're not looking at the entire tube, another relationship that comes out of setting those two things equal to each other, except now we use local convection coefficients. Okay, so that surface temperature minus our mean temperature at any location x over surface temperature at our mean inlet, okay, is equal to the exponent of negative perimeter times length, times x over mass flow rate times heat capacity times our average convection coefficient. Okay. So the point here being that you can use any combination of these things, okay, knowing how to solve for your convection coefficient with Nusselt number in order to solve for any missing term. So let's say you're missing your surface temperature, or let's say you're missing your mean outlet temperature. Okay, well, it's easy enough then to isolate one of those two and solve for it. Okay. Now all that's left to do then is to solve for Nusselt number. Okay, and I expect at this point you'll be able to do that with the equation sheet. So as an example, for laminar, fully developed, constant surface temperature conditions, your Nusselt number is 3.66. Okay, and so on and so forth, right? If you have developing conditions, and you watch the last video, you'll see how to solve for those, but for constant temperature, right? And same with turbulent flow, okay? And you have that, ultimately, really, you're going to want to use, and you have that Nusselt number tree diagram. Okay, that basically feeds you how to get this Nusselt number, where you're still calculating your Reynolds number and these locations first. Okay. Now, in both of the previous situations, we've basically assumed that the outside is insulated. Okay, but in the very final video, I go through a case where I actually have some heat transfer mechanism caused by external flow over the cylinder, where I'm also passing a fluid through it. Okay, and in that case, instead of finding an average convection coefficient, I can find an overall convection coefficient, okay, which incorporates the effects of what's going on outside and inside here. Okay, so you had a problem like that on quiz 8, okay, and you'll see that this appeared in an example problem that I've put up in the next video.